Palm Beach, Florida, January 1905. The morning air carried the salt tang of the Atlantic as spectators gathered along Ormond Beach to witness the impossible. Automobiles racing at 90 miles per hour across hard-packed sand. Steam hissed from overheated radiators. Steel ground against steel as mechanics made final adjustments. The crowd pressed forward, expecting another demonstration of European automotive superiority. Then Louis Chevrolet's French Fiat lost control. The machine cartwheeled across the beach in a spectacular cloud of sand and twisted metal. While other spectators rubbernecked at the carnage, one American engineer walked methodically through the debris field. Henry Ford picked up a bent valve stem, no bigger than his thumb, 30% lighter than American parts. Yet when he tried to break it over his knee, nothing. The metal bent like putty but refused to snap. Every major American steel producer would soon tell Ford the same thing. Can't be done. Not commercially. The infrastructure didn't exist. The expertise didn't exist. European metallurgy was generations ahead of American capabilities. But that fragment of impossible French steel would trigger the most decisive materials revolution in automotive history, proving that sometimes the greatest American innovations begin by stealing European secrets and making them better. Ford climbed down from his Model K race car, its engine still ticking from the morning's speed trials, and surveyed the wreckage scattered across 200 yards of Ormond Beach sand. The French Fiat had disintegrated with surgical precision. Hood panels here, wheel assemblies there, transmission components forming a perfect arc where momentum had carried them. Other spectators clustered around Chevrolet, who was walking away from the crash with nothing worse than bruised pride and sand in his goggles. But Ford ignored the drama, drawn instead to the mechanical puzzle spread before him. He moved through the debris field with the methodical pace of a man who had spent his boyhood dismantling pocket watches, cataloging each piece by weight and function. A crankcase here, cast iron, probably German. Brake drums there, standard carbon steel, unremarkable. Then his boot struck something that rang with a different tone. Ford knelt and extracted a valve stem from the sand, brushing away the grit with calloused fingers. The part weighed exactly what he expected, except it was 30% lighter than equivalent American components. Ford held it up to the Florida sunlight, studying the metal's grain structure through its bent surface. Clean brake lines where stress had exceeded material limits. No brittle fracturing, no crystalline failure patterns that plagued American racing parts. This steel had deformed predictably, absorbing energy instead of shattering. Alexander Winton appeared at Ford's shoulder, breathing hard from his jog across the beach. "Spectacular crash," he panted, mopping his forehead with a silk handkerchief. "French drivers always push too hard. That's what you get with European showboating." Ford extended the valve stem toward his chief rival. "Look at this." Winton barely glanced at the twisted metal. "Broken part from a broken car." "What's your point, Henry?" "Try to break it." "What are you, 12 years old?" But Winton took the valve stem anyway, gripping it with both hands. He applied steady pressure, expecting the steel to snap cleanly. Instead, the metal bent further, forming a neat U-shape without cracking. Winton frowned and reversed his grip, trying to straighten the part. It returned to within 5 degrees of its original configuration. "Probably just good French craftsmanship," Winton said, tossing the valve stem back to Ford. "Americans don't need European gimmicks. Our steel mills produce the finest metal in the world." Ford caught the part and slipped it into his coat pocket. Around them, track officials were clearing the remaining debris, preparing the beach for the afternoon time trials. Steam rose from overheated radiators as mechanics adjusted fuel mixtures and checked tire pressures. The familiar sounds of American automotive competition, wrench strikes on stubborn bolts, engines coughing to life, drivers shouting instructions to their crews. But Ford's attention had shifted to something invisible, something that existed in the molecular structure of the metal fragment now warming in his pocket. Carbon steel running 60,000 to 70,000 pounds per square inch had built the Brooklyn Bridge and the world's tallest skyscrapers. It was American steel, reliable and proven, that had launched the industrial age. So why couldn't American metallurgy match whatever the French had discovered? The question gnawed at him during the drive back to Detroit, through 3 days of business meetings, and into the following week when he finally summoned his chief metallurgist to the Piquette Avenue plant. Child Harold Wills arrived carrying a leather satchel stuffed with technical manuals and a perpetually skeptical expression that had served him well in his 27 years of solving impossible engineering problems. "CH," Ford said without preamble, pulling the valve stem from his desk drawer. "Find out all about this. That is the kind of material we ought to have in our cars." Wills examined the part with the concentrated focus of a man who understood metal at the atomic level. He scraped a small sample with his penknife, noting the way the shavings curled rather than flaking like typical carbon steel. He tested the part's flexibility, measuring the force required to bend it and the percentage of springback when pressure was released. Finally, he looked up at Ford with the expression of a man who had just discovered a fundamental law of physics had been violated. "This isn't standard carbon steel," Wills said. "There's something else in the alloy, something that's changing the molecular matrix. Can you identify it? Give me 2 weeks." Wills disappeared into his laboratory with the enthusiasm of a prospector who had found gold traces in an unexpected stream. He subjected microscopic samples to chemical analysis, heat treatment experiments, and stress testing that pushed the metal beyond normal operational limits. The results defied conventional metallurgical wisdom. The French steel contained trace amounts of vanadium, a rare element that Ford had never heard of, and Wills had encountered only in academic papers from European research institutes. At concentrations of just 0.2%, vanadium transformed ordinary steel into something extraordinary. Instead of failing catastrophically when stressed beyond its limits, vanadium steel absorbed energy and returned to shape. It was 30% lighter than carbon steel, but could withstand nearly 3 times the stress before permanent deformation. "It's impossible," Wills reported, spreading his test results across Ford's desk. "By every principle of metallurgy I understand, adding such a small amount of any element shouldn't produce this dramatic a change in material properties." Ford studied the numbers: tensile strength, compression resistance, fatigue limits that exceeded anything American steel producers claimed possible. "But it works." "It works. The question is whether we can make it work here." That question led Ford to contact every major American steel producer, from Carnegie Steel's massive Pittsburgh operations to Bethlehem Steel's integrated mills. He described vanadium steel's properties, provided sample analysis, and offered substantial contracts for regular production quantities. The responses were unanimous: "Can't be done, not commercially." Carnegie's chief metallurgist explained the thermal requirements. Vanadium demanded furnace temperatures of 3,000 degrees Fahrenheit. American blast furnaces maxed out at 2,700 degrees. The infrastructure didn't exist. Republic Steel's president outlined the economic impossibility. Retooling furnaces for exotic alloy production would cost hundreds of thousands of dollars with no guarantee of market demand. Bethlehem's engineering committee declared vanadium an interesting laboratory curiosity that would never prove viable for mass production. Ford listened to each rejection with growing frustration, recognizing the same conservative thinking that had dismissed automobiles themselves just 10 years earlier. These were the men who had built America's industrial might through incremental improvements and proven methods. They saw no profit in chasing European metallurgical experiments that might disrupt established production systems. But sitting in his office with Wills's test results and the bent valve stem that had started everything, Ford realized he wasn't just chasing better steel. He was chasing the future of American manufacturing itself. His then vision of a universal car, affordable, durable, and mass-produced, required materials that could withstand punishment while remaining light enough to keep costs down. Standard carbon steel was too heavy and too weak. The French had cracked the code. Now Ford had to steal it, perfect it, and scale it beyond anything European manufacturers thought possible. By spring of 1906, Ford had exhausted his list of major steel suppliers. Carnegie Steel's board had voted unanimously against vanadium experiments, citing excessive risk to established production systems. Bethlehem Steel's president wouldn't return Ford's telephone calls after their engineers calculated the infrastructure costs at over $2 million. United States Steel dismissed the project as chasing European racing novelties with no commercial applications. Ford sat in his Paquette Avenue office, staring at a map of American steel production facilities marked with red ink, every rejection, every closed door, every expert who insisted that vanadium steel belonged in European laboratories rather than American factories. The established industrial giants had built their empires on proven carbon steel formulations and saw no reason to risk disrupting systems that generated reliable profits. Then Wills knocked on his door with a telegram from Canton, Ohio. "Republic Steel Company," Wills announced, reading from the yellow paper. "They want to discuss your vanadium requirements. Meeting next week if you're interested." Ford had never heard of Republic Steel, which probably explained why they were willing to take his call. A train ride to Canton revealed a scrappy operation run by engineers who understood what it meant to compete against industry giants through technical innovation rather than market dominance. Republic's president, James Campbell, was a Scottish immigrant who had worked his way up from furnace operator to company ownership by solving metallurgical problems that stumped university-trained engineers. "We can't match Carnegie's volume," Campbell admitted, walking Ford through Republic's compact but well-maintained facility. "But we can do things they won't attempt: custom alloys, experimental processes, projects the big companies consider too risky for their standardized operations." Ford studied Republic's furnaces, smaller than the massive installations at Carnegie's Homestead Works, but equipped with modifications that suggested creative engineering. Oxygen injection systems to boost combustion temperatures, refractory brick formulations designed for specialty applications, crucibles lined with materials Ford didn't recognize. "Can you reach 3,000 degrees?" Ford asked. Campbell exchanged glances with his chief metallurgist, an intense young man named Robert Archer, who looked like he spent more time with blast furnaces than barbers. "Not with our current setup, but we can modify the equipment. Question is, what's it worth to you?" Ford's answer surprised even himself. $47,000 for furnace modifications, plus guaranteed orders for 2,000 tons annually once you achieve commercial production. The sum represented Ford's entire startup capital from 1903, everything he had risked to launch Ford Motor Company. Campbell and Archer disappeared into urgent consultation, emerging 20 minutes later with handshake agreement to attempt what America's largest steel producers had declared impossible. The furnace modifications began immediately. Republic's engineers stripped out standard refractory brick and replaced it with experimental compositions that could withstand temperatures that would melt conventional furnace linings. They installed oxygen injection systems borrowed from European smelting operations, with pressure regulators that could boost combustion temperatures by controlling airflow precisely. New crucibles arrived from specialized manufacturers, lined with exotic materials that cost more per pound than finished steel. October 1906 brought the first vanadium heat. Ford and Wills traveled to Canton to witness what they hoped would be the birth of American vanadium steel production. Republic's workers had been preparing for weeks, stockpiling coal and adjusting furnace parameters through dozens of small test runs. Campbell and Archer moved through final preparations with the nervous energy of men who understood they were betting their company's survival on untested metallurgy. The furnace reached operating temperature at dawn, its interior glowing white-hot through observation ports that hurt to look at directly. Workers fed raw materials into the crucible, iron ore, carbon, and precious vanadium compounds imported from European suppliers at costs that made Ford wince. Temperature gauges climbed past 2,700 degrees, then 2,800, finally reaching the theoretical minimum of 3,000 degrees required for vanadium integration. For 6 hours, the furnace consumed coal at rates that would bankrupt smaller operations. Steam hissed from cooling systems as workers adjusted oxygen flow and monitored temperature fluctuations that could ruin the entire batch. The industrial symphony of American steel production, hammers striking hot metal, steam engines powering massive bellows, workers shouting instructions over furnace roar, filled the Canton facility with sounds that had built the nation's infrastructure. Then disaster struck. The extreme heat turned most of the vanadium into worthless slag, leaving behind steel that contained less than 0.1% vanadium, not enough to matter. What little metal emerged from the crucible demonstrated none of the flexibility and strength that Ford had witnessed in the French valve stem. Republic had successfully reached 3,000 degrees, but the metallurgy remained beyond their understanding. Ford stood in the furnace yard, watching workers rake slag from the failed heat, and calculated the cost of his gamble: $47,000 in furnace modifications, imported vanadium compounds at European prices, 6 tons of coal burned to produce steel that was barely superior to standard carbon formulations. The Detroit Free Press would soon note with satisfaction that even Ford makes mistakes. But Wills was already deep in consultation with Archer, analyzing the chemical composition of the failed steel and adjusting parameters for the next attempt. Lower the pour temperature slightly. 3,000 degrees was necessary to melt vanadium, but excessive heat destroyed the molecular bonds they needed to create. Adjust the carbon content to provide proper matrix structure. Most critically, add the vanadium at precisely the right moment during the cooling process, when the steel's molecular structure was receptive to integration. "One more heat," Wills told Ford as they prepared to return to Detroit. "We understand the failure now. Next time will be different." Ford looked at Republic's modified furnaces, still radiating heat from the day's disaster, and made the calculation that would define his company's future. He could accept the loss, abandon vanadium steel as commercially impossible, and return to proven carbon steel construction like every other American manufacturer. Or he could double down on the bet that systematic American engineering could perfect what European laboratories had discovered. "Schedule the second heat for November," Ford told Campbell, "whatever it costs." November brought unseasonably cold weather to Canton, with frost coating Republic Steel's windows as Wills arrived for the second vanadium heat. He had spent the intervening weeks analyzing every aspect of the October failure, consulting European metallurgical journals, and corresponding with German steel researchers who had attempted similar experiments. The problem wasn't just temperature, it was timing, chemistry, and the precise sequence of operations that transformed raw materials into the molecular matrix they needed. Archer met him at the furnace with a revised plan that addressed each failure point from the previous attempt. Instead of maintaining maximum temperature throughout the entire process, they would reduce heat to 2,900 degrees once the vanadium began integrating with the iron matrix. Carbon content would be adjusted to 0.4%, high enough to provide hardness, low enough to maintain flexibility. Most critically, they would add the vanadium compounds during the cooling phase when the steel's molecular structure was crystallizing into its final form. 18 hours of continuous operation, Archer warned as workers began feeding coal into the furnace. "Once we start, we can't stop until the pour is complete. Temperature fluctuations will ruin everything." The furnace reached operating temperature at dawn, its interior blazing with intensity that turned Republic's foundry floor into a landscape of shadows and glare. Workers moved through choreographed routines they had rehearsed dozens of times, adjusting oxygen flow, monitoring crucible temperature, preparing the specialized molds that would receive America's first successful vanadium steel. Steam rose from cooling systems as the facility's steam engines powered massive bellows that maintained precise combustion conditions. Ford arrived from Detroit at midday, finding Republic's entire workforce focused on the single furnace that represented their company's future. Campbell paced the foundry floor like a general monitoring a crucial battle, consulting temperature gauges and conferring with Archer about chemical reactions occurring inside the white-hot crucible. The air itself seemed charged with possibility and the metallic taste of industrial ambition. By afternoon, the furnace had consumed 4 tons of coal and reached the critical moment when vanadium compounds would be introduced to the molten steel. Archer supervised personally, adding measured quantities of vanadium oxide at precisely calculated intervals. Each addition sent showers of sparks cascading from the furnace mouth as exotic metals integrated with American iron ore in combinations that had never been achieved on commercial scale. The pour began at sunset, with molten steel flowing into molds at temperatures that required workers to wear protective equipment borrowed from glass manufacturing operations. Unlike the October disaster, this steel moved with the smooth consistency that indicated proper molecular integration. No excessive slag, no separation of materials. The vanadium was bonding with the iron matrix exactly as European research suggested it should. But the real test came when the steel cooled enough for chemical analysis. Wills worked through the night with sample specimens, measuring vanadium content with precision instruments borrowed from Republic's Quality Control Laboratory. The results exceeded every expectation, exactly 25 hundredths of 1% vanadium distributed evenly throughout the steel's molecular structure. When tested for tensile strength, the steel hit 170,000 pounds per square inch, exactly matching the French valve stem that had started Ford's obsession. But Ford demanded more comprehensive testing before celebrating success. He wanted to understand how vanadium steel behaved under different stresses that automobiles would encounter on American roads. Wills subjected sample bars to compression testing, twisting them until conventional steel would have snapped. The vanadium specimens bent beyond 90 degrees and returned to within 5 degrees of their original shape. Torsion tests revealed similar resilience. The steel absorbed energy that would fracture carbon steel and released it gradually as the metal returned to its unstressed configuration. Most remarkably, fatigue testing showed that vanadium steel could withstand repeated stress cycles that would crack conventional materials. Wills subjected sample rods to thousands of flex cycles, simulating the constant vibration and impact that automobile components experienced during normal operation. Carbon steel samples failed after 3,000 cycles. Vanadium steel was still performing perfectly after 15,000 cycles. Ford studied the test results with the satisfaction of a man who had bet everything on superior technology and watched systematic engineering triumph over conventional wisdom. Republic Steel had achieved what Carnegie and Bethlehem declared impossible: commercial production of vanadium steel that exceeded European specifications. But as Ford examined the numbers, he realized Republic had given him more than better steel. They had created smarter steel. Traditional carbon steel failed in one of two predictable ways. It bent permanently if too soft, or snapped cleanly if too hard. Vanadium steel occupied the engineering sweet spot that Ford had been seeking since his first automobile experiments: strong enough to resist deformation under normal loads, flexible enough to absorb exceptional stresses without catastrophic failure. This revelation transformed Ford's understanding of what automobiles could become. Instead of designing vehicles that avoided stress, he could build cars that absorbed punishment and continued operating. Instead of restricting automobiles to smooth roads and careful driving, he could create machines that thrived on the rough conditions that characterized American transportation infrastructure. The implications extended beyond individual components to Ford's entire manufacturing philosophy. With vanadium steel, he could build lighter vehicles that were simultaneously more durable. Reduce weight without sacrificing strength. Create automobiles that ordinary Americans could afford to purchase and maintain, rather than expensive machines that required constant professional attention. Ford contracted for 2,000 tons of vanadium steel annually, with options to increase production as his manufacturing volumes grew. Republic Steel committed to maintaining quality standards that exceeded European specifications while developing new alloy formulations optimized for specific automotive applications. Campbell and Archer would work directly with Ford's engineers to create custom vanadium compositions for different vehicle components. By early 1907, Ford Motor Company was consuming more vanadium steel than any manufacturer in the world. The Model N, incorporating vanadium components throughout its chassis and drivetrain, weighed 1,050 pounds compared to 1,400 pounds for equivalent competitors. Sales jumped from 1,700 cars in 1905 to 8,500 in 1907 as customers experienced the superior durability that vanadium steel provided. American automotive engineering had not just matched European innovation, it had surpassed it through systematic improvement and commercial application that European laboratories never attempted. The impossible metal from a French racing accident had become the foundation for American manufacturing supremacy in the emerging automobile age. The Panic of 1907 struck American industry like a financial earthquake, toppling banks from New York to San Francisco and destroying industrial fortunes that had taken decades to build. Stock prices collapsed by 50% in 3 weeks. Railroad companies defaulted on bond payments. Steel production plummeted as construction projects were abandoned and manufacturing orders evaporated overnight. Ford watched the crisis unfold from his Paquette Avenue office, tracking steel prices that fluctuated wildly as desperate suppliers sought any buyers willing to honor existing contracts. Carnegie Steel laid off 30,000 workers. Bethlehem Steel shut down entire production facilities. The industrial giants that had dismissed Ford's vanadium experiments were now fighting for survival in markets that had vanished almost overnight. Republic Steel found itself hemorrhaging money on specialized vanadium operations that served a single customer in an industry many experts predicted would collapse entirely. Campbell telephoned Ford with increasingly desperate updates: bank credit lines canceled, raw material suppliers demanding cash payments, workers threatening strikes over delayed wages. The modifications that had enabled vanadium steel production now seemed like expensive mistakes that would bankrupt the company. "We might have to shut down the vanadium furnaces," Campbell admitted during a particularly grim conversation. "Standard carbon steel at least has multiple buyers. Vanadium is too specialized for a market this unstable." Ford understood the mathematics of Campbell's situation. Republic had invested everything in equipment that served essentially one customer. If Ford Motor Company failed during the financial crisis, Republic would own the world's most expensive scrap metal. The smart business decision was to abandon vanadium production and return to conventional steel that could be sold to multiple industries. But Ford also understood that retreating to conventional materials would doom his vision of mass-produced automobiles that ordinary Americans could afford. Vanadium steel wasn't just superior engineering, it was the foundation for manufacturing processes that would revolutionize American transportation. Abandoning vanadium meant accepting permanent second-tier status behind European manufacturers who had already perfected the metallurgy. Instead of cutting costs, Ford made a decision that stunned his business partners. He used the 1907 financial crisis to buy out wavering investors at depression prices, gaining complete control of Ford Motor Company. Then he committed the company's remaining resources to a single enormous bet: a new automobile that would demonstrate vanadium steel's superiority so dramatically that no customer could ignore the difference. Meanwhile, competitors were using the financial crisis to attack vanadium steel's reputation. Ransom Olds, whose Oldsmobile company represented conservative engineering philosophy, began spreading concerns about untested materials in consumer products. "Vanadium is too new," he warned automotive journalists. "Nobody knows how it ages under real-world conditions. What happens when these experimental cars start failing after 2 or 3 years?" The attack found its target when a Model N suffered a highly publicized axle failure in downtown Detroit, stranding its owner in heavy traffic and requiring a team of horses to tow the vehicle to safety. Newspapers covered the incident as evidence that Ford's European innovations were failing American customers. Orders plummeted as potential buyers questioned whether vanadium steel could be trusted for daily transportation. Ford and Wills investigated the failure personally, traveling to the repair shop where the damaged Model N sat with its rear axle twisted into an S-curve that would have snapped conventional carbon steel cleanly. But the vanadium steel hadn't snapped. It had deformed exactly as designed, absorbing energy that would have caused catastrophic failure in standard materials. "Look at this," Wills said, pointing to the damaged axle. "Carbon steel would have broken into 2 pieces, probably launching the rear wheels into traffic. The vanadium steel bent but held together, keeping the vehicle controllable." The investigation revealed improper heat treatment at Republic Steel, a single batch of axles that had been cooled too rapidly, creating internal stresses that compromised the vanadium's molecular integration. It was a quality control failure, not a fundamental problem with vanadium metallurgy. But public perception focused on the dramatic photographs of twisted axles, rather than the technical explanation of why the failure had been survivable. Ford realized he was fighting a war on 2 fronts: financial crisis that threatened his supply chain and public relations disaster that questioned his fundamental engineering choices. Conventional wisdom suggested retreating to proven materials and conservative designs that wouldn't challenge customer expectations. Every business advisor recommended abandoning vanadium experiments and focusing on reliable carbon steel construction. Instead, Ford doubled down with a commitment that bordered on recklessness. He announced development of an entirely new automobile that would be built around vanadium steel's unique properties rather than simply substituting superior materials into conventional designs. This vehicle would demonstrate American engineering superiority so convincingly that customers would demand vanadium steel rather than questioning its reliability. The financial commitment was staggering. Ford contracted with Republic Steel for increased vanadium production during the worst economic crisis in decades. He hired additional metallurgists and engineers when other companies were laying off workers. Most significantly, he committed to developing 20 different vanadium alloy formulations optimized for specific automotive applications. High-carbon vanadium for crankshafts requiring hardness, low-carbon vanadium for axles needing flexibility, medium-carbon compositions for chassis components that demanded both strength and machinability. Wills supervised the alloy development program with obsessive attention to molecular engineering that pushed vanadium steel beyond European specifications. Each formulation required separate heat treatment protocols, different cooling rates, and specialized handling procedures that Republic Steel's workers mastered through months of trial and refinement. The complexity exceeded anything attempted in American metallurgy, but Ford insisted on perfection rather than compromise. By late 1907, Ford Motor Company was consuming vanadium steel at rates that would have supplied entire European automobile industries. Republic Steel had become completely dependent on Ford's orders, abandoning most conventional steel production to focus on exotic alloys that no other American manufacturer understood or wanted. The gamble was either visionary or insane, depending on whether Ford could create an automobile so superior that customers would pay premium prices during America's worst financial crisis in decades. Everything depended on proving that systematic American engineering could transform European innovations into products that redefined what automobiles could become. The vehicle that would vindicate or destroy Ford's vanadium. Obsession was already taking shape in engineering drawings and prototype components. It would be called the Model T, and it would either establish American manufacturing supremacy in the automobile age or bankrupt the company that bet everything on impossible steel from a French racing accident. October 1st, 1908. Ford stood in the Piquette Avenue plant watching workers assemble the first production Model T, its black chassis gleaming under electric lights that had replaced the gas flames of earlier manufacturing operations. 29 different vanadium steel components formed the vehicle's skeleton, each piece engineered to exploit the metal's unique properties rather than simply substituting superior materials into conventional designs. The Model T represented 3 years of obsessive engineering that transformed Ford's vanadium gamble into systematic manufacturing advantage. Instead of building another automobile that happened to use better steel, Ford had created a machine designed around vanadium steel's ability to absorb punishment and return to shape. Every component reflected this philosophy, from crankshafts that could twist through stress loads that would snap carbon steel to chassis members that flexed with road impacts instead of transferring shock to passengers. Wills supervised the final assembly with satisfaction that came from solving impossible metallurgical puzzles through systematic American engineering. The high-carbon vanadium crankshaft could withstand torsional loads of 12,000 foot-pounds, triple the stress that destroyed conventional engines. Low-carbon vanadium axles absorbed road shocks that would fracture standard steel, distributing impact energy through controlled flexing that protected wheel bearings and suspension components. But Ford's greatest innovation lay in optimizing 20 different vanadium formulations for specific applications throughout the vehicle. Medium carbon vanadium for transmission gears that required both hardness and impact resistance. Ultra-low carbon vanadium for spring steel that needed maximum flexibility without permanent deformation. Each alloy pushed Republic Steel's metallurgy beyond anything European manufacturers had attempted. The Model T's performance specifications read like fantasy compared to conventional automobiles. Front axles designed to support 1,200 pounds of vehicle weight tested to 4,800 pounds without failure, a 4-to-1 safety margin that no competitor could match. Rear axles could twist through 180 degrees and return to true, absorbing impacts that would disable standard vehicles permanently. Ford backed these claims with the most audacious marketing promise in automotive history. Built for any road, any load, any weather, proclaimed advertisements that challenged customers to find conditions the Model T couldn't handle. It was industrial bragging that would either establish American manufacturing supremacy or destroy Ford Motor Company if the vehicles failed to meet their ambitious specifications. The real test came not in Ford's factory, but on America's primitive road system, where Model T automobiles encountered conditions that European engineers never imagined. Railroad ties laid across muddy tracks served as bridges in rural areas. Creek beds became temporary roads during seasonal flooding. Farmers used their automobiles to pull stumps, power threshing equipment, and transport loads that would overwhelm vehicles designed for European cobblestone streets. Model T owners discovered that vanadium steel transformed these challenges from potential disasters into routine operations. Axles that bent under extreme loads straightened themselves when stress was removed. Chassis members that flexed over obstacles returned to proper alignment automatically. The vehicle absorbed punishment that would strand conventional automobiles and continued operating as if nothing had happened. The vindication Ford had sought since 1905 arrived through thousands of customer experiences that validated his vanadium obsession. Epo, Montana rancher, wrote to describe driving his Model T through a boulder field that destroyed two competitors' vehicles, with nothing worse than scratched paint to show for the ordeal. A Michigan logger reported using his automobile to skid timber loads over terrain that would have broken carbon steel axles within hours. But the most dramatic proof came during Ford's own testing program, where company engineers subjected Model T vehicles to abuse that deliberately exceeded any reasonable operational expectations. They drove automobiles off loading docks to test impact resistance. They towed loads that tripled the vehicle's rated capacity. They operated in temperature extremes from Minnesota winters to Arizona deserts, documenting performance that no competitor could match. Between 1908 and 1915, Ford captured 48% of the American automobile market through superior engineering that customers could experience in every mile of operation. The Model T's durability became legendary not through advertising claims, but through demonstrated performance under conditions that disabled competitive vehicles. The production numbers told the story of American manufacturing triumph. Ford produced 15,000 Model T automobiles in 1909, 78,000 in 1912, and over 500,000 by 1916. Each vehicle contained those 29 vanadium steel components that had started as a French racing secret and evolved into the backbone of American automotive supremacy. Republic Steel expanded its vanadium operations to supply Ford's massive production volumes, becoming the world's largest producer of specialty steel alloys. Campbell's company, which had nearly failed during the 1907 financial crisis, now employed over 3,000 workers in operations that served customers across multiple industries who had discovered vanadium steel's advantages. The Model T's price dropped from $825 in 1908 to $290 in 1925, making automobiles accessible to ordinary American families for the first time in history. This democratization of transportation resulted directly from vanadium steel's properties. Vehicles lasted longer, required less maintenance, and operated reliably under conditions that would destroy conventional automobiles. Ford had achieved something unprecedented in industrial history. He had taken a European innovation, perfected it through systematic American engineering, and scaled it beyond anything its inventors thought possible. The vanadium steel that began as microscopic traces in French racing components now formed the foundation for mass transportation that would reshape American society. By 1927, Ford had produced 15 million Model T automobiles, a manufacturing achievement that demonstrated American industrial capacity to the world. Each vehicle validated the engineering principles Ford had discovered in a debris field on Ormond Beach, proving that the right materials mattered more than conventional wisdom, established suppliers, or expert opinion. The legacy extended far beyond automobiles. Vanadium steel became standard in construction, aircraft manufacturing, and industrial machinery as American engineers applied Ford's lessons to other applications. The metallurgy that experts had dismissed as European racing nonsense transformed into fundamental technology that supported American industrial dominance throughout the 20th century. Modern automobiles, optimized for fuel economy over durability, represented a retreat from Ford's engineering philosophy: aluminum suspension components that shatter under stresses. Model T axles absorbed routinely, cast parts that fail catastrophically instead of bending and returning to shape. Weight savings achieved at the cost of the flexibility that had made automobiles truly reliable. Ford's greatest innovation hadn't been the assembly line or mass production techniques that historians typically celebrated. It had been proving that American manufacturers could identify superior technology anywhere in the world, improve it through systematic engineering, and scale it beyond what anyone previously imagined possible. The vanadium steel revolution had transformed a nation of farmers into a nation of drivers, one unbreakable axle at a time.